All right, and then finally, my very last story has to do with the Gaia satellite. And this is a satellite that was launched by the European Space Agency. And its purpose is basically to create the most accurate map of our galaxy ever by accurately measuring the positions and the distances of about 1 billion stars. So that's still less than 1% of our galaxy. But as you'll see, this is still a much more substantial undertaking than anything that we've done. And so Gaia follows a long, rich tradition in astronomy going back thousands of years when the Greek astronomer Hipparchus first created the first star catalogue, but he measured only 850 stars. And as you go through the centuries, you find other astronomers using their naked eyes measuring on the order of about 1,000 stars and trying to accurately map them in the sky. John Flamsteed in 1725 came up with the first catalog that used an actual telescope to make the measurements. And so he had a catalog of 3,000 stars, and then over time, others after him came up with catalogs that measured more and more stars and were more accurate because their telescopes were better. But it was really only in the 19th century that astronomers were able to measure distances to stars using the parallax method, which is basically trying to see how stars shifted against background stars because of the Earth in its motion around the sun. And so the very first attempt to do that, those astronomers were able to measure the parallaxes of 3 stars. But then over time, we had astronomers who measured distances to hundreds of stars, then thousands of stars. And then in the early 90s, the Europeans had another space mission, in this case, Hipparchus, named after the very first astronomer who made an atlas of stars. And in this case, they measured over 100,000 stars. And then finally, we get to Gaia now, whose mission is to map and measure 1 billion stars. And these lines here give you a sense of how accurate these stellar distances are. And so we go from not so accurate to pretty accurate to Gaia, which will give us really, really good accuracy. Some of you might have seen this in the news in the past month. This was a map of the sky that was released by the Gaia team. And what they did was, this is actually a map of all the stars that they measure, so all billion plus stars. And the brightness of this map basically corresponds to more and more stars. So the large and small Magellanic Clouds are places where they measured lots of stars, and this looks really bright. The plane of our Milky Way looks really bright because they measured lots of stars, but there are also gaps. These are places where there are molecular clouds. So those clouds I was talking about in that earlier story. And Orion is right here. You can actually see the Orion A cloud over there. And then all these other weird artifacts are actually due to the way that the Gaia satellite scans the sky. So these aren't real, these are just artifacts. Now, what is really neat about Gaia is that in addition to measuring the positions, it actually can measure the colors of stars really accurately. And when they do that, they can classify the stars based on what's known as the Hertzsprung-Russell diagram. And this HR diagram is a way that astronomers use to figure out where stars are in their evolutionary state. So it turns out that most of the stars in the sky lie on what we call the main sequence. And so if you can figure out the colors of stars along here, and also know what the absolute brightness of the star is, you can actually plot a star along somewhere in this diagram, and stars spend about 90% of their lives along this main sequence. And so here is our sun, and as you go up in this direction, stars get more massive and hotter. And then when stars die or they evolve towards the end of their lives, and before they die in a supernova or in or they throw out their outer shell to form a planetary nebula, these stars migrate off the main sequence into the supergiants and the giant stages. And then for stars that are like our sun, after they go through their death throes and throw out off their outer envelopes, they end up what are known as white dwarfs, meaning they end up in this region of the HR diagram. And previous to Gaia, when astronomers tried to map all the white dwarfs that are relatively close by to our sun, so within about 300 light years or so, we've only discovered about a couple hundred, so in the order of about 200 white dwarfs that are relatively close by and in this region of the diagram. Well, here is what Gaia's Hertzsprung-Russell diagram looks like. And so you can see millions. I don't know if this includes all 1 billion stars, but after a certain point, obviously the stars start to overlap each other. But you can see that instead of just a couple hundred points, there are literally tens of thousands, if not millions, of white dwarfs that have been discovered by Gaia. And this particular story looked at just the closest ones, and so what they found were just under 14,000 white dwarfs, all within a distance of a couple hundred light years, so under 300 light years towards the sun. And what they find is that they actually see structure in the white dwarf population. And you can't really see it here, but we'll see it in just a second. And so what they did was this structure in the HR diagram comes about if there are different properties to the white dwarfs. And so this team ran computer simulations with different star formation rates, with different amounts of hydrogen and helium in the atmospheres or the upper layers of these white dwarfs. And what they find is that they actually have two different models. And so you kind of see this bifurcation in the models. And it actually matches the observations pretty well. So again, these smaller points are from the computer simulations, and these bigger points are from the Gaia observations. So these are those 13,000 plus white dwarfs that are all relatively close to us. And what they find is that this bifurcation can be explained by different amounts of hydrogen and helium. But what's also really neat is that there's also a brightness difference between, it turns out that, let's see, the brighter white dwarfs are up here and the dimmer ones are down here. And it turns out that there are actually two different populations, one more massive than the other. And so this plot basically measures the masses of the white dwarfs. And so there's a population of white dwarfs that are close to 1 solar mass, and then there's another population that's closer to about 0.6 solar masses. And it turns out that you can't get this population, you can't normally make white dwarfs this massive unless they come about via a merger scenario. And so this is the first evidence that we have that, or substantial evidence involving thousands of stars, that white dwarf mergers are pretty common in our universe.